Okay, so I'm going to carry on the theme of mining, and now we're going to sort of think really broadly and look at the biogeochemical and health impacts of mining. So let's look, again, why, I'm sure everyone knows this, but why do we need mining? Let's remind ourselves why. Let's think about what happened in the past, what's going on now, and then some ideas for the future. What we can do as geoscientists. So why do we need mining? Well, I think everyone knows this answer in this room. Here we've got some nice items. We've got some nice bicycles, some slightly old mobile phones, and some solar panels. So they all have something in common. What do they have in common? They're all green technologies. I suppose the mobile phone is not quite green, but we use phones in our everyday lives now, and they're made of metal. We don't recycle enough metal at the moment to supply the world's needs. To keep our society going and to keep making these green technologies, we need metal. If it can't be grown, we can't grow metals, so we must mine them. Mining is essential if we want to maintain our lifestyles at the moment. Why do we need mining? Well, we use a lot of mined materials to make a lot of our beautiful art, like King Tut's mask in ancient history, artworks, buildings, all the things we need to support our modern lifestyles. It makes jobs for people. We're here because of mining and geology, of course. It makes money, GDP, supports cultural development, schools, infrastructure, and it gives us scientific knowledge. So there's a lot of really good things about mining. And here's some more. We've seen some of these already. An international workforce, so sending people around the world to collaborate, acts as a catalyst for other industries. So when you've got a mine, other industries grow up around the mine. And it can drive sustainable development as well. So mining is essential, and I think some people don't realize that, not in this room, but this is a message we try to promote at the Camborne School of Mines. But of course there are negative sides, like anything, to mining. It can create pollution or contamination. We know that for sure. If the mining is done by a company that then takes the money out, that doesn't leave anything behind for the country. It can use up energy. Mining uses an awful lot of energy. Some things I forget sometimes. But it's not just the mining, it's the energy resources that we're using. It can displace people, it can cause problems for people, it can kill them. Human rights can be violated in some areas with mining practice, wars, and it can create poverty. So we recognize that these are negative aspects to mining, and when I come to the end, we're trying to now hopefully work towards lessening a lot of these impacts. So let's think about the past. No environmental legislation that we know about. Maybe in Antiquity there was, but we don't know there was. And little human health or safety protection. So these are just some random pictures. The picture up there, mining for metal, is a picture that's stored in the collection of the Science Museum in the UK in London. And they've got a lot of very nice pictures representing various stages of science throughout history. So I particularly like this one because this man has been mining really hard. He's been underground, working really hard, and he's brought out a lot of ore. So it's just showing you that this happened in the past, just like today. You need to mine a lot of rock to get the valuable material out because we know the grades are not low. So even then, mine waste was generated. So mine waste has been around a long time, and mining impacts. It's just the mining at that time was a lot smaller scale than it was then in the Industrial Revolution. This is ancient slag from Cyprus. So slag is the glassy material. It looks like lava from Hawaii. It's the glassy material left over after the ores have been burned or roasted. And you remove the valuable material, like some of the metals, copper and nickel and so on, and you're left with this glassy waste. This can also contain toxic elements, so lots of arsenic and vanadium and so on, and it's a waste as well. It's a fairly big problem, not as big as tailings, but you see a lot of ancient slag. In Cyprus, there's a spot called Skoriatissa, which is, I think, still operating. And outside the gates of Skoriatissa, there's a huge pile of this slag, a few meters high. And geologists in Cyprus from the Geological Survey Department have dated this slag. So they've been able to work out the history of mining in Cyprus. And what they've realized from that slag is that Cyprus must have been deforested about 10 times to make the copper from Antiquity. So it's even then had a fairly big environmental impact. Maybe not so much pollution, but changing the ecosystem. Now we go to England. So this is in northeast England, where lead mining has been taking place at least for 2,000 years. The Romans, we know, mined lead. But the big change in lead mining was in the Industrial Revolution. So around 1750, when the industrial industry got going in England, around the world, and the lead mining just went crazy. Lots of lead mining going on. And this is an example of how a river system can be impacted. So in the early stages of mining, the river wasn't impacted. When we get into the heart of the Industrial Revolution, you can see the river is clogged with mine waste. All the waste went into the rivers. There was no legislation. So big channel change, lots of material, lots of lead. But after mining stopped, so around 1976, no more waste is going in and the river is re-equilibrating again. But it's a huge impact on that system, on farmers in that system. And actually now, today, these rivers in this beautiful area of England have a lot of lead in the floodplain. Luckily, the lead is locked away in minerals that are not very reactive, so it's pretty stable, we think, most of the time. So other examples of past mining activity, this is a very famous Klondike gold rush in the late 1800s. And there were a lot of gold rushes around from about the 1850s onwards. People were having trouble economically. They wanted to become rich really quickly. And so in 1898, there was reports of gold in the Yukon Territory in northern Canada. And there was a mad rush of people from all over the world. So they had to climb over mountains that you can see here. This is called the Chilkoot Pass, to get to a lake, to then go to the lake and go to the gold fields. It was very arduous. So this is in Alaska, in the US. When they passed over the top, they went to Canada. And the Royal Mounted Canadian Police saw these people and said, look, you're not coming into Canada unless you have 2,000 pounds on your back of supplies, so you don't starve. So these people would have to go up and down this mountain pass many, many times, packs on their back, to bring enough supplies to do mining. So it had a huge impact on the people influx into this area. You can see once they got to the gold fields, they cut down all the trees, and they mined the gold using sluice methods like a planning, and they, again, really destabilized the ecosystem in the mining. And then 2 years later, it was all over. They went to Alaska for another gold rush. So it was a very short-term impact, but quite a devastating one on the environment. This is Rio Tinto now in Spain, in the southwest of Spain, where mining has been going on for 5,000 years at least. And the area is quite contaminated by mining, but this is something we also remember from mining. There's not only the waste and the devastation at some times, but the buildings and the infrastructure that left behind. So these are historic buildings. You can actually see Roman tunnels in the waste here as well. So that's actually kind of a good and a bad thing. You've got this material left around, but it represents heritage. And heritage is one really important thing about the past mining. We want to understand how past peoples live. We have pride in our areas where we've had mining. So in Cornwall, where I live now, the whole area of mining has been declared a World Heritage Site because of the mining heritage. So that's kind of turning something that's a waste or a problem into a good museum, a natural museum, and that's happening a lot more. So I'll take you to Cornwall now, just to show you a couple of other effects. So this is Heartlands. This was a big area in western Cornwall that was really the heart of the tin and copper producing areas from about 1850 to about 1920. And this is what it looked like, rather bleak and lots of chimneys. You can see how many mines there are, lots of individual mines, mining veins that contain tin and copper. So another typical thing is all the air pollution that's produced, and again, just the industrial sort of wasteland that can be produced from mining. On the health side, we know that human health protection wasn't regarded as very important, and this is an example of that. So in Cornwall, as in many places, arsenic, hard to believe, but arsenic was actually mined. So these veins that contained tin and copper also contained arsenic, and they mined the arsenic by roasting or heating up the ores with arsenopyrite, and then they had sort of long chimneys where they collected the vapors, and the vapors crystallized into arsenic trioxide, so arsenic 3+, a powder, which is actually really toxic. So they collected that and they sent it to US to control the boll weevil on cotton. So to kill off this pest in cotton, they produced arsenic. So you can see this worker, he's got his own clothes on. He just went to work in his own clothes. He's not wearing gloves. He has a handkerchief around his mouth, and that's all. Normally they use quite young children, so he's a little bit older, and these boys were scraping the arsenic off the walls. So they didn't live very long. They were killed by the arsenic. So all these examples. So we know that the mining practices were important, but not always good practice. In the present, though, where we are today, we have these legacy impacts. So we have the waste, not from our mining, but from old mining. We know there's a lot of waste around, and we have that to deal with. But we also have impacts from mining that are going on today. And let's think about how things changed that much. And I think the answer is no in some cases, but yes in others. So we're sitting on the fence. Today we recognize that mine waste and mining, it's a global issue. Almost every country, maybe not Antarctica, but almost every country in the world either has a mining industry now or had one in the past. So there is a legacy of mine waste, no matter what. Even if it's small scale, there is a legacy. So take you around the world again. You've seen the Rio Palmar already. Here's the Grey River running with tailings in the dry season. Here's the Rio Tinto in Spain, which is an amazing place to go if you're interested in geochemistry, mineralogy, and actually microbiology. The Rio Tinto is 80 kilometers of pH 2 water that looks like that the whole way. And that's from all those years, the centuries of mining, thousands of years of mining, and poor management of the waste at the time. In Cyprus, we have the slag, but we also have open pits that have now filled with water. We call them pit lakes, and sometimes it's acid water because they were sulfide mines. Here's a modern mine in Western Australia in Kalgoorlie. It's a big gold mine. You can see it's the super pit, so it's a super big mine. But you can see that the footprint of the mine and all the waste is almost as big as what we can see of the town. So mining, even today, still has impacts. We know that. We know the legacy waste is impacted on river systems. I've already talked about that. So here's the Pilcomayo again. And a term that was made in, I think, the 1980s was this idea of chemical time bombs. They were trying to really make it exciting. And really what that means is you've got all this sediment. We don't know how deep. Could be a meter or more, contaminated with arsenic and antimony and thallium and mercury. And every time you have a big flood, which you do in the wet season, all of that moves around. So you can move this bomb downstream and cause problems in bigger areas. This is in northeast England where we've had lead mining, and we've got these areas where there's just not enough money, there was no remediation done. You've got waste that's just sitting there without caps, and it can be rained on, and you can have a lot of leakage from these wastes into river systems. Fortunately though, this is quite old now, it's 100 years old, and it has been leached so much that it's quite stable, both in terms of physical and chemical effects. So it's not as bad as some situations. We know that the landscape is impacted. So we're left with legacy of medieval tin mining in Cornwall. You can see these pits here. This is all from the medieval times, around the 1400s in Cornwall. In a really beautiful area. It's on the high hills, very nice to walk. And that tin streaming has left an imprint on the landscape. And we still see that today. If I just push that forward, this is St. Austell. This is in middle part of Cornwall. Well, clay mining for clay for making ceramics is still carried out. And you can see there's still quite a big footprint, although they're doing a lot of work to remediate that now. So we've still got a lot of the same issues going on. We still see contamination from mining. So here's historic alluvium from old alluvium that's been moved. And its concentrations of cadmium, copper, lead, and zinc are higher than what are recommended by the Dutch, at least. And here's a recent spill, the Asna spill, where the tailings were just as contaminated as the old alluvium. So we're still left with a lot of the same issues. If we look at some global, think big now, look at the global statistics. The amount of mine waste, people have said the amount of mine waste we're generating now is bigger than any time before. And that's because we're mining lower grade deposits, big deposits. So if you go to Chile, they're mining open pits that are about 4 kilometers long and 2 kilometers wide. They're massive. The copper grade is about 0.3%. So we're generating even more waste. Some people say 14 billion tons of tailings per annum. That's a lot of material to try and deal with. Studies on tailings dam failures show that the impacts have significantly increased. They're bigger tailings dam failures. bigger impacts and longer impacts on river systems. But there are good things, and I'm going to come back to some of these good things. There is a lot more movement to look at waste as a resource. So going back to look at tailings when maybe the extraction wasn't very efficient. So maybe there's a lot of copper or gold left in tailings. Let's look at these as waste rather than, or sorry, as resources rather than waste. And let's use tailings and other materials like cement. So there's a revolution going on, a slow one, but there's funding for this, and it's starting to happen to try and turn around things. Acid mine drainage. So the acid drainage that you see, this is a Rio Tinto again, generated largely from the oxidation, the breakdown of pyrite, is a global problem as well. This is the biggest problem that mining companies face. If you have a new mine coming on, one of the things you have to do is assess your waste to see how much acid they're going to produce. If they are going to produce acid, you need to have a mechanism in to stop that acid forming. Otherwise, you won't get your permit. This is some remediation of acid mine drainage using lime. And these are some acid mine drainage minerals in Cyprus. So it's really everywhere. The global liability cost there of 100 billion, I think, is far too low. When we wrote an issue of Elements in 2011, we tried to get a figure for it, and that's what we came up with. People have since told me it's much, 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 much higher than that. So we have a site in Cornwall called Wheel Jane. And Wheel Jane receives acid mine drainage from a number of underground tunnels into one place. It's treated like this with lime to generate sludge. And they figure out that they're probably going to have to do that for at least 100 years and maybe forever to keep going, because the acid mine drainage is still being generated. So it is a big problem. We're starting to recognize, again, that dusts are something we need to think about. These are dusts from historic tailings in Washington. So the tailings dam have been left alone, no cover, and creating dust. And this is modern dust. So dust, again, is something that everyone's starting to think about. You've already heard the tailings dam story. Again, we think that tailings dams are increasing in their severity. And the interesting thing for me is not only are they increasing in severity, but they're actually having global impacts. So in small-scale tailings dam, you affect a river in a country, that's for sure. But in this case, this is the biggest tailings dam failure on record. 32 million cubic meters of tailings. This is iron ore tailings again, so they're not that toxic. But the interesting thing for me is that it went 600 kilometers from the mine, and it got into the Atlantic Ocean. So now it's a global problem. That material, okay, it's going to be dispersed, but you're spreading it around the globe. So we're having global impacts. We know there are human health effects from mining. There have been in the past. Here's some examples modern day. This is from the issue of Elements. This is in Nigeria, where people grind gold ores to make money in their huts. You can see the dust, but it releases lead. Lead is a really well-known toxin. It especially affects children and their development, and there are cases of lead poisoning. This is a Realgar mining area in China, where up to 2011 they were still mining arsenic, and the local people are coming out with arsenic poisoning symptoms. So black spots, thickening of the skin, cancers. There are no mine waste human health or animal health effects as well. And this is an interesting one because it's an effect both modern, from modern flooding, but from legacy historic mine waste. So in 2012 in mid-Wales, in the west of the UK, there were a series of really sharp floods. So we get these floods now that happen in 2 hours, and there's so much water that it just moves everything around. And so my colleagues in Wales went out and sampled sand or sediment in the rivers and analyzed the lead. You can see there's a lot of lead, more than 30,000 milligrams per kilogram being moved around. Unfortunately, they noticed that there were some cattle deaths at the time. And what had happened was the cattle had eaten the freshly deposited lead material and ingested it, and also the lead over time had gotten up into the grass. So they were able to prove using lead blood and lead isotopes that it was related to this episode. So we know there are some human health effects. What we don't know is how broad these human health effects are. So I know you've been doing some studies in Slovenia looking at the health effects of mercury. And in some cases, effects might not be bad. We just don't know. So here in Cornwall, this is a geochemical map of arsenic in soils. And you can see the red areas. There's quite a lot of arsenic in Cornwall. That's not surprising. Some of it is natural background, just from the rocks, but a lot of it is from mining. So we know they roasted the arsenic ores. I'm sure a lot of this arsenic is from the smelter or the fallout. What we don't know is if there's any human health effects. No one's ever done the study that we know about. So hopefully there are no effects. No one has really said anything. It's something I'm thinking about maybe doing. Again, you've got areas like this where you've got the arsenic-rich dusts in California, which can be dry at times, blowing around. We don't know if there are health effects. If there are, we need to do something about it. But we just don't have the know-how in it. We know it's expensive to do these studies. In Bolivia, we were able to show that the crops were probably okay. So more studies like this. But there is a turnaround going on today, really good turnaround. So this is a pyramid produced by Bernd Lodemoser. And it was based on landfill, actually, but he's converted it to mine waste. So the idea is the best option is at the top, and at the bottom is the least favored option. So in terms of generating mine waste, the best option is to not generate mine waste. That's very difficult in some cases. You have to generate mine waste. There are some types of mines that you can use solutions. So in Canada, to get potash out of the deep ground, they inject fluids, and then they bring the fluids up, take out the potash, and they do have a little bit of waste, but it's mostly no waste. But that's really hard to do. The next best option is to reuse the waste or recycle it, try and get energy from it, and then the worst option, of course, is to treat and dispose. So if we can find new ways to use the waste and store it safely, that's the most ideal thing. And I think the turnaround is coming. So you do see remining of tailings. This is gold tailings in Africa, I believe. Hydraulically mining the old tailings to get gold out of them. Remining coal. So coal that's been sort of mined or left behind, remining, and then re-landscaping as well. Trying to recover metals from waste. So this is a project funded by our government in the UK, up in the beautiful Lake District in the northwest of England, gorgeous area, where we've got some mines left over, and Newcastle University and the Coal Authority, who looks after all metal mines as well in the UK, funded a study for a pilot system, and it's been really successful at removing metals. So they remove these metals at the moment into a sludge, and then they let the water go back into the system. It's clean. The next thing they're doing is seeing whether they can then get the metals out of the sludge and reuse them. So there are lots of these things going on at the moment. There are efforts to reprocess tailings. So this is an interesting site up in the Bolivian Altiplano. It's got the good and the bad. So you've got tailings falling in the river still. There's a tailings pile here that's unmanaged. So that's causing issues. But the local peoples have built buttle pits. So that's a Cornish word. A buttle pit is a big pit that you see there, and you basically stir it around, and then you hydraulically let the heavy minerals settle, and you skim off the light minerals. So what these local people are doing are working on these tailings to get metal out of them so they can make some money. So they're actually reprocessing those tailings right there. We know there are lots of technologies to take metals out of acid mine drainage, and that's becoming more and more popular. Let's make some money out of this and treat the drainage at the same time. So I think the future is carrying on this way. I think we're going to always have bad practice in mining, and hopefully we can eliminate that over time. That's the goal. So we want to work on these new insights, or at least I'm trying with my team and my colleagues to try and look at these and help promote this idea that we can do mining better. Let's look at the effect of mining on global biogeochemical cycles. Is there an effect? Maybe there's no effect. That's great. If there is, let's do something about it. And also, let's think about mining and health. Let's keep ourselves healthy by doing mining the right way. So what I'm going to show you is a number of initiatives that I've been at the Camborne School of Mines for 2 years. So I'm trying to get these all going. I came from London beforehand. Okay, so the first one is to look at acid mine drainage. So acid mine drainage, as I said, is one of the big problems around the world. So my niece is also a geologist, which I'm really happy about. And she came and worked with me for a couple of months one summer in between her education. And I said to her, why don't we start trying to compile global statistics on acid mine drainage and start to think about where it is and what the fluxes could be. So she did this. She got a start on it, but she had to go and work on other things too. So this is where she got to. This is for zinc. So it's showing you the fluxes of zinc dissolved in acid mine drainage. So again, you can see she couldn't find any data for Africa, and she sort of didn't find much for some of these areas. But in Europe, there was quite a lot, in North America and so on. So we have a few dots here just to get going. You can see actually that a lot of the big dots are in Europe, and this is from historic mining. The biggest one is the Rio Tinto. That's not surprising. It's 80 kilometers of acid mine drainage. And studies in the past have said that 60%, that's huge, of the global zinc flux, the global zinc dissolved, is coming from that area only. That's enormous. We need to think about that. So when I started at Exeter, I got some funding, and I've got a young man who's really good, and he's putting together a GIS database of acid mine drainage. And actually, he's starting with Europe, because the world is a bit too big to start with. So he's checking all the papers and all the data. He's using remote sensing to map acid mine drainage waters, and he's got a database of mines, so he can link the acid mine drainage to the mines. And the idea is to come up with a model. Where are the sources of acid mine drainage? What are the big fluxes of acid mine drainage? Then we're going to link it to databases to biodiversity. Does it have an effect? So we want to do this, is it having an effect on iron cycling? Or we know that sulfate moves around as well. Is it accelerating weathering? These acid waters can accelerate weathering. So Richie's just started, and he's almost finished his Europe thing, and we're starting to see these patterns plus some other ones. So, and then we'd like to extend it globally as much as we can, anyway. So that's the water side. On the sediment side, and I know you've done this in Slovenia, is to try and quantify where the mine waste is on the world. So this was started again in London. I had a postdoc working with me, Soren Balaban, and he used Google Earth, just Google Earth, and we went to the Pilcomayo where we've worked before, and he was able to map the contaminated sediment, the mine waste sediment, in the Pilcomayo using Google Earth. He was able to say the red areas that you see here are where agriculture is going on. And then when you see a down arrow, that's deposition of tailings. Where you see an up arrow, that's where there's erosion. And the red areas highlight where there's deposition of quite contaminated sediment. So these can be used almost as hazard maps to say, oh, be careful of agriculture here. This is a really contaminated area that's still receiving mine waste. And then we got a figure for the amount of mine waste, the area. We don't know how deep it is, so we know the area of mine waste in this basin. And this is just one basin. So again, this is a dream. Let's see if we can kind of get an idea of where the mine waste is. If we can sort of highlight areas that really need attention. We can give these to companies and say, look, these are all potential resources. Why don't you go and have a look at them and bring everything together. Together with that, saying we can also use these maps for hazard mapping. So this is a river swale. This is one of the lead-affected areas in England. And based on the chemistry, but also the morphology of the river, and knowing where the big deposition areas are, we can highlight these red areas that are the really hazardous areas that farmers could use to try and avoid grazing on. The other thing is to try and get a perspective on which sort of pollution we really need to be attendant to. So on the left, we've got some of the tailings dam failures, and we've got volumes of material. So here's the really big one in 2015. Here's Mount Polly, and then you can see the others are much, much lower. On the right-hand side, I know I don't have much data on here, but it's an idea. You can see the amounts in the Pilcomayo, in northeast England, and a site in the US. Because we don't know the thicknesses in these floodplains, I've made an assumption. The blue is if it's 1 meter thick all over. The red is if it's 2 meters thick. And what you can see is even if it's blue or red, the volumes of what we say chronic discharge, so that's just tailings that go in periodically, that volume is bigger or the same as some of those tailings dam failures. So while tailings dam failures get all the headlines, and they should, we also have to remember these river systems have contaminants from other mining. So we need to be aware of those, not to scare people, but to try and manage them properly. So you've seen this map before. It's different colors now. And this is our tailings dam map again. And again, we're trying to determine what are the risks to human and ecosystem health. Here we've got a few other colors showing you where most of the tailings dams are. So more than 90% of tailings dams are in China. Everywhere else that we know about at the moment. And again, the white areas we have no data for. But you can see there's a lot of tailings dams most places, and we just need to be aware of where they are so we can determine the risks to human and ecosystem health. Right, this next one is slightly an academic one. So this is thinking about cycles, global biogeochemical cycles. So when we know that climate change is one of our big issues at the moment. That's without question. And a lot of that understanding has come from understanding the carbon cycle. So what are the forms of carbon? Is it CO2? Is it limestone? Where is the source? Where does it move to? How much moves? And so this idea is to take that model, that idea of a global biogeochemical cycle, and apply it to mine waste. And again, can we use this for management? So the concept, this is done for zinc, is we know the mine waste starts at mine sites. That's probably certain. And using zinc, we've got zinc in a sulfide form, zinc in a carbonate form, and zinc in other minerals, so minor amounts of zinc. We can work out a number of mine waste roughly based on how much material is mined globally, so we have an idea of the volumes. We know where mine waste can go. It can go in the atmosphere as dust, and it takes different forms. So as it moves, there are geochemical reactions that change the original zinc into other forms that might have implications for health. There's the atmosphere. It can go in the hydrosphere. So if it's in an acid mine drainage, it can be dissolved. I haven't got an arrow. It can go into the biosphere. Oh, there it is. So it can be taken up in plants. So some plants will take up zinc into their bodies. We don't know how much of that happens. Or humans. We know zinc can go into river systems. And again, the forms change from the original ore minerals often to secondary minerals that hold the zinc. From rivers, that material can go to the oceans, and everything ultimately ends up in the ocean, probably, as a cycle. We know that it's a cycle because ocean materials are then subducted, eventually over geologic time. So someday, all that mine waste that ends up in oceans will be subducted, and not in our lifetime, but in geologic lifetime, it might come up as a mine again. So this is the idea of this cycle. Can we quantify? Can we think about where our mine wastes are going and how much are going? And can we control it? So we want to use it for protection, again, for global health, identifying areas for recycling and protecting agriculture. So thinking sort of big way. The other thing is, can we look at health? So planetary health is a big, human and planetary health is a big issue at the moment. There's some new journals out on it. Can we do the studies with our colleagues, with our epidemiology colleagues, with our doctors and so on, to understand if there are any impacts on health, and if there are, should we do something about it? So I've mentioned in Cornwall we have a lot of arsenic. And this is a site in Cornwall, not far from the university, that's open. It's quite about 1% of arsenic in this waste, and it's used as a bicycle training place for children. And Cornwall, although it is wet a lot of the time, there is dust at times. And of course, these kids are exposed to the arsenic. So we could work out risk models for those kids, but also would want to know, is that arsenic going to be harmful to them in the long term? We don't know. There's been a little bit of study started by people in Manchester, actually, looking at arsenic in urine and arsenic in wells. And there is elevated arsenic in these areas. So is there going to be a health effect from this arsenic? Should we know? Should we do something about it? So I think working across the disciplines is a great way to go. And then, of course, this is what we do at the Camborne School of Mines, and we should all be doing this, promoting this idea of sustainable mining. So sustainable mining is a bit of a funny term, I admit, because can mining really be sustainable? You're taking something out of the ground and you're using it for something else. The answer is probably not perfectly. But I think a nice way to think about it is can we move toward it? Can we try to move towards being as sustainable as possible? And we can do this using all of these practices. First of all, to mine, it has to be economic. Otherwise, someone's not going to put the money in to invest in the mining. So it has to be economic. And we recognize that. But at the same time, can we practice good safety to protect people? Can we get the community involved We should. It's their land. It's their resource. When the mining finishes, the mine will leave and the community will be there. They should be involved. Can we use the resource efficiently? Can we produce as little waste as possible? Can we use that waste for something else? Can we protect the environment? And I think there is a lot more movement towards this. A lot of the big companies around the world now have a vice president of sustainable mining. So the thought process is changing. It will take time, but I hope it will. The other thing at the Camborne School of Mines and other places is to think about this thing called the mining value or the mining chain. So the idea is when you're mining, you go out and you find a little thing that you like, you stake a claim, so you acquire the property, you do the exploration, you plan your mine, you carry out your mine, and then you process your material, and one that I forgot is eventually you close your mine. That's a traditional chain of mining. The environmental protection used to be here, right at the end. Let's worry about that after, doesn't matter. And community involvement, well, sometimes it never happened. The idea now is to get the environmental protection and the community involvement all the way through. So from the very first point of you thinking that you might have a mine, you should be thinking about the environment and the community as well. And again, this is happening, so it's really good. So if you're going to mine an area, what you should ideally do is do a lot of surveys like you do here, of the geochemistry, of the air, of the plants, to find out what the baseline conditions are before you actually mine. Then once you start mining, you can look at the impacts relative to the baseline. And again, having the community involved means that the mine is part of the community rather than something separate. Okay, so that one didn't take too long. So mining has been, and I still think it is vital for everything that we do in our society. We know the past environment and health protection hasn't been great, generally poor. Today, we've got that legacy, and there's still poor practice going on. But I think there's a big shift. We're going to lessen those impacts, and hopefully in the future, companies and in our universities, we can carry out scientifically studying the impacts of mining, promoting good remediation, quantifying these impacts, and protecting the environment and human health. And ideally, in my opinion, can we move towards this idea of sustainable mining so that we can continue to enjoy our lifestyle and continue to be healthy and have a healthy environment as well.